periodic table is a collection of work of many men. For many years, scientists tried to group the properties of all the known elements together into one big lump sum and try to order and structure the periodic table. The look that the periodic table has now is the culmination of all that work. It has been changed many, many times and been moved around to fit the needs of the scientist. The current most accepted periodic table model that you see here below was actually developed by a guy by the name of Dmitry Mendeleev. We'll learn about him more down the road, but he came up with this idea, this structured pattern. Now, the big idea with this pattern here is that it's a repeating pattern, and it's a repeating pattern of the properties. And that's the major focus of this whole thing. The actual order of the elements on the periodic table was actually set in motion not by Mendeleev, but by a guy by the name of Henry Moseley. And we'll talk about him more down the road as well. Generally speaking, there are several different ways to look at the periodic table. The first thing first, anytime you have any type of vertical column, like this, for example, here is a vertical column, that's called a group. Members of the same group are vertically aligned. On the other hand, talking about a horizontal row, this right here is called a period. Period has to do with the energy level. And again, we'll go into more depth down the road with this, but in terms of energy, it means basically the distance away from the center of the atom, the nucleus. Groups, however, are what we tend to focus on more when we talk about the periodic table, because members of the same group have very, very similar properties. Group 1A, right here, minus hydrogen, are called the alkali metals. These violently react in water. Group 2A, right next door, are called the alkaline earth metals. Those are most commonly found combined with oxygen in nature. Skipping over those and moving to the outside, we have group 6A over here. Group 6A is oxygen's family. Those are called the chalcogens. Very, very easily to combine. We have group 7A, extremely reactive. These are called the halogens, which means salt former. And last but not least, we have the noble gases. Noble gases have very similar properties. They're very inactive, inert. They do not readily combine with one another or anything else for that matter. We can further break down the periodic table into three major overriding categories. The first one is the nonmetals. Nonmetals, outlined here in green, tend to be brittle. They tend to be very colorful. They're found in all three states of matter, solid, liquid, and gas, but most commonly in the gaseous form. Hydrogen, for example, oxygen, nitrogen, these are all gases, all the noble gases. They are small in terms of their variety, in terms of number of different types of nonmetals, but very, very high in terms of their abundance around on Earth. The greatest diversity on the periodic table exists in the forms of the metals. There are lots and lots and lots of different types of metals out there, great variety of them. And though these make up only a small percentage of the total amount of elements on Earth, there is a great variety. Now, a lot of the metals, aside from the alkali metals and the alkaline earth metals, exhibit very, very similar characteristics. And we'll talk about those down the road. But some of the things that you know about metals are true. They do conduct heat and electricity very well. They are bendable. You can shape them. That's called malleable. They're also able to be pulled into thin wires, and that's called ductile. And though they differ in certain colors, most of them have a very shiny appearance to them. Between those two categories, we have a third category of metal. And this third category of metal are called the metalloids. And though you might not think about metalloids as being terribly important, they are very important, despite the fact that there's only a few different types of them. For example, silicon is an extremely important metalloid that's used in the production of computer chips. It's also one of the major components of glass and quartz. So though there are not many in variety, they make up a great deal. Now, the big thing with these metalloids is they exhibit properties of both metals and nonmetals. Now, what that does not mean, it does not mean that they can change their properties under different conditions. What it, however, does mean is that boron might exhibit some properties that are more similar to nonmetals and a couple that exhibit to metals. And on the other hand, you might have tellurium that's the reverse of that situation. There's also another special group of elements on the periodic table. And I really shouldn't say group. It's a cluster of 7 elements that don't exist as single elements at any point. Just like most of the population of Loganville High School is made up of single birth people, there do exist other groups out there. And the most common other groups of people out there are twins. Well, there are actually twins in the periodic table. There are 7 elements that I actually put together into a little pseudonym here. We have the Brinkelhoffs. These 7 elements right here do not exist anytime in nature by themselves. Whereas you can go out and find an atom of carbon, you can never find an atom of bromine. Bromine is always Br2. Iodine is always I2. Nitrogen is N2. Chlorine is Cl2, and so forth and so on. All of these things here will separate from their twin to form a compound with a different element, but when left by themselves, they'll never actually be by themselves. They will always combine with their twin and form a molecule instead of an atom. Ions are charged atoms. So any atom with a charge is no longer called an atom. It's called an ion. And the way that you get an ion is by gaining or losing an electron. It's important to remember that if you gain or lose a proton, you change the element and what you have there. And if you gain or lose a neutron, you're not talking about changing anything with the identity, you're just getting heavier or lighter, and that would be your isotope. Now, when you gain or lose an electron, you cause an imbalance in the charges. For example, if you look at sodium, sodium is Na. Naturally, sodium will have 11 protons and 11 electrons. And the most common isotope of sodium has 12 neutrons. Sodium is also in group 1A. And group 1A tends to lose 1 electron. So when sodium loses 1 electron, it changes to 10 electrons. In that case here, we have 11 positive charges and 10 negative charges. Therefore, the overall charge that sodium will take will not be Na even, it'll be Na with a +1 charge. All of the group 1A elements will form a +1 charge. All of group 2A will take a +2. And you can see the trend as you move across what are called the representative elements. This group here and these 6 groups here are called the representative elements. And you can see the charges. What we have going on there in the middle is something altogether different. These are called the transition metals. And the transition metals can actually form pseudovalence electrons. And because of that, they have variable charges. And you have to learn what those charges can be. Now, where ions come into big importance is when we're talking about ionic compounds. And ionic compounds are all around us. From the salt you put on your French fries, to the baking soda that maybe you use to deodorize your fridge. Now, ionic compounds are formed by ions coming together. And it's all about the transfer of electrons, specifically the outermost electrons, called the valence electrons. So it's the transfer of electrons. And that transfer results in a charged entity. And those charged entities combine together to form compounds. When an atom loses electrons, it becomes positively charged. So lose electron equals positive, and that's called a cation. When an atom gains an electron, that makes it negative, and that's called an anion. When we form an ionic compound, we are going to combine the cations and the anions in a way that the overall net charge of the compound will equal 0. Think back to the location in the periodic table of these elements. If you think back to where lithium is, It's in group 1A and therefore it takes a +1 charge. Oxygen's in group 6A, so it forms a -2. Now, in order to make these charges balance each other out to a net charge of 0, we need to have more than one lithium. In order to make it work, we actually need 2 lithiums. So if we had 2 lithiums, each one containing a +1 charge, each one would in theory be giving the oxygen 1 electron. Overall then, we have 2 lithiums present and 1 oxygen. Note that on our compound here, there is no final charge because the final net charge is equal to 0. Looking at the second example, we have aluminum. Aluminum's in group 13 or group 3A and therefore takes a +3 charge. Sulfur's in group 6A with oxygen takes a -2 charge. Now another easy way to make this thing work is to crisscross and reduce. If I circle the number of the cation and the anion and I reverse their positions, I get the lowest whole number ratio that gives us our compound. In this case here, our compound formed will be Al2S3. You could still look at it mathematically. If I had 2 aluminums, I would have a +6 charge. If I had 3 sulfurs, I'd have a -6 charge. When placed together, they would equal a whole number 0. That's all we have about ionic compounds in the periodic table. Please bring any questions that you have into class tomorrow.